Hello everybody and welcome to Climate Change Unit 2. In the first unit of this course, we learned a lot about the mechanism of how the climate works, as well as how we humans are changing it. In the second unit, we're going to take a look at the historic and prehistoric climate conditions on Earth, as well as what changing these conditions today will do to different systems. We're going to start off, though, by looking at some variability within the climate system and how that impacts us in our daily lives. Come on along. Our quote for today comes from Francis Rooney, congressman from Florida's 19th district, who says, "I'm a conservative Republican and I believe climate change is real. It's time for my fellow Republicans in Congress to stop treating this environmental threat as something abstract and political and recognize that it's already affecting their constituents in their daily lives. By the end of today, you will be able to explain the difference between weather and climate and how climate is able to impact weather." A couple of things coming up. First, you have your greenhouse gas lab due in just a couple of class periods. And next time we have our third journal club meeting, for which you should prepare by reading the IPCC Summary for Policymakers, taking notes, writing down your questions, and filling out your handout. Last time we were together, we took a test over Unit 1 material. And the first thing we're going to do when we get to our live Zoom class is we're going to pass those tests back. You're going to look at the questions you got wrong, talk with your group, figure out the correct answers. And if you can't figure that out, then when we get back together as a whole class, we'll have time for discussion. So, we're going to recap really quickly before we start new stuff. First thing is that the atmosphere and ocean are fluids, which means they can move, we can transfer energy. And the horizontal distribution of energy causes these fluids to move. We can see this movement as weather or as ocean currents. We know that energy starts near the equator and moves towards the poles via both atmospheric circulation in our Hadley, Farrell, and polar cells, as well as through ocean currents. This is an important part of the climate system because this energy movement is weather, and weather is how we feel the climate day to day. Weather is going to change because we are changing the distribution of heating and increasing the energy in the system. There is a ton of internal variability in the climate system. How you experience climate today, weather, is different than how you experienced it yesterday. The weather changes. And this is because mostly of natural variability. You've got solar variability, you've got volcanic activity, and then you've got all the internal dynamics of the atmosphere and ocean, how those interact, and then how the atmosphere, ocean interact with land and ice. And all of those things together cause our weather. Natural variability does not mean that this will remain constant as climate changes from anthropogenic causes. If we want to think about climate variability, we can think about persistent patterns of weather. You can have long periods of rain which cause floods. You can have long periods without rain which cause droughts. We've taken that persistent pattern of weather and it has created this relentless experience for you as you are looking at the weather. The weather is not always appearing to be random. And there's a whole bunch of different causes of climate variability. We've got things that you're familiar with, like seasons and El Nino. But there's others as well, like North Atlantic oscillation, Pacific decadal oscillation, annular mode. There's internal variability in the climate system, and this causes change. It's important, though, to think about these events on the scale that they belong. We experience weather on a day-to-day scale, but we experience climate over much longer periods of time. Right? We talk about climate as being, what you can expect to experience from weather over a 30-year time frame. And so when we're looking at climate change, we're not looking at what our weather is today. We're looking at what the climate today, that average of weather, now is compared to what it was at one point in time and will be at some point in time in the future. And so if we look at short-term things, we've got, on a handful of year time scales, you've got things like El Nino and Arctic oscillation and Pacific decadal oscillation. And sometimes these cause certain regions to warm up or cool down. But we should not confuse these short-term patterns with long-term trends. And that's important for us to not make that confusion, because we make decisions about energy security and elections based off of oftentimes short-term experiences, because these long-term consequences appear to be far away. When we think about how to address climate change as a society, it's good to think about this in terms of what we can do. If I build a new road or a new pipeline, that infrastructure investment will have a certain length of an impact. What is its working life? If I build a wind turbine or solar panel or a car. And it's important to think about these in terms of how they're going to relate to an accumulation of wealth, of an individual over a lifetime, of society, how these things over their long term are going to be impacting the planet. Let's start looking at an example of variability of which you are very familiar. We've got seasons, right? You've got cold winters, you've got warm summers, and just because it's getting colder in the fall, of course, does not mean that next summer won't be warmer than the one before, because the pattern is it always gets colder in the winter. And in between the winter and the summer, you've got these seasons of spring and autumn, and that is kind of messy. Sometimes they're warm, sometimes they're cold. They sometimes have extreme amounts of precipitation. And this is where we tend to see the most clear changes as a result of climate change. Of course, you hear more about extreme events here and here because they push us outside of where we would expect to ever be in our life. But if you can have a larger extreme event occur here without people taking as much of a notice. You've probably heard about El Nino before. A lot of times we hear about it in the context of what it's going to do to impact us, and we don't hear too much about its mechanism. So here's a little bit about El Nino Southern Oscillation, or ENSO. And ENSO is an atmospheric and oceanic phenomenon which occurs because the trade winds along the equator are blowing from east to west. And as they do that, they push the water and cause the water to build up on the western side of the Pacific Ocean. And so if we were to measure the distance of the western side of the Pacific Ocean from the center of the Earth and the eastern side of the Pacific Ocean to the Earth, despite the fact that water normally forms a level surface, the western Pacific will be farther away. So you've essentially built yourself a hill of water on the western Pacific. And that hill is held there by the trade winds pushing it west. And of course, as you push that water west, you've removed water from the east, and water has to come back to fill that place. And so where does it come from? It comes from the depths. And so you get along the coast of South America an upwelling. So we're bringing cold water up from the depths along the coast of South America. As a result of this, there's lots of great things that happen here. You've got hugely productive seas because all the nutrients that sink to the bottom have been brought up near the surface where they are exposed to the sun, and you get flourishing of plankton and fisheries. And this is a really productive area of cold water right at the equator. However, if we have a change in the trade winds, this pattern gets messed up. If the trade winds relax for a period of time, if something causes the trade winds to blow less strongly, the water in that hill of water is unable to be held in the western Pacific. And so when those winds drop, that falls back because the water wants to be level, and we get a countercurrent of water running eastward across the Pacific. And so instead of having a buildup of cold water along the coast of South America, we end up having that warm water flood in and take its place. This shift stops upwelling along the coast of South America, which has major consequences to fisheries, but it also changes atmospheric convection patterns dramatically, which has impacts in North America, pretty far away from this, can experience El Nino events. You have the opposite condition can occur as well. We call this La Nina, and if we have unusually strong trade winds, we push more water to the west, create stronger upwelling, and you get a greater decrease in temperature. This impacts us here in the United States. You get warmer winters in Canada and the northern U.S. It gets wetter in the southeast, drier in the northwest and Ohio Valley, and it's warmer. Look, we look at the trend of years. Here's an El Nino. Can you look at the other data points in this graph and identify where other El Nino events might have occurred?
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Nino. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern U.S., and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Nina, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Nina can lead to drought in the southern U.S. and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Nino and La Nina together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the U.S., but in many parts of the globe.
That's El Nino, which we will often refer to as ENSO. And you've probably heard about that one a lot, but you might not have heard of Pacific Decadal Oscillation. This is atmospheric and oceanic, a lot like El Nino, except for it's in the northern Pacific. And instead of it lasting, about a year, like El Nino events do, it lasts 20 to 30 years. And also, unlike El Nino, we don't really know how it works. But you can look at it and you can see the warm and cold trends. And so we can have a warm or positive phase, or we can have a cool or negative phase in that as well. If you're in the warmer positive phase, you get warmer than average temperatures in the Pacific Northwest. In southern North America, you get cooler temperatures. Because we're not creating energy, we're just moving it around. The Pacific Northwest gets more precipitation. However, Siberia, Australia, and Canada get less. And so we have these impacts which are worldwide. And we can expect those to happen on the 20 to 30 year cycles. Another source of internal variability within the Earth system is the North Atlantic Oscillation. And unlike ENSO, which is atmospheric and oceanic, NAO is purely atmospheric. All that NAO is the strength of the pressure difference between the Azores high and the Icelandic low. And if we take a look at these images, we can see that the Azores high, which is a high pressure system situated between the Hadley and Faroe cells where you'd expect one to be, that sits above the Azores Islands. And over Iceland, we have a low pressure system right where you'd expect one to be between the Faroe and polar cells. And if there's a large difference between the pressures of these two systems, we can say that we are in a positive index. And if we have a small difference between our high pressure and our low pressure, we can say that we are in a negative index. The North Atlantic oscillation is the biggest impact of winter climate variability in the North Atlantic. This is a fairly regional effect, so we tend to only be seeing impacts on the east coast of the United States and in Europe. What is the impact of having a large or small pressure difference between the Azores high and the Icelandic low? Well, if you have a large pressure difference, you can expect stronger winds and therefore more storms to traverse the North Atlantic. You know that air tends to flow from high to low pressure, and so this helps drive these storms across the ocean. Because these are coming from the southwest to the northeast, they tend to bring warm and wet winters to northern Europe, and we end up having cold and dry winters in northern Canada and Greenland. The US gets mild and wet winters on its eastern coast. Now, if we have a negative index, so there is not that big pressure difference, well, there is nothing that's forcing that moist air that's traveling across from the west to the east across the Atlantic to the north. And because of that, northern Europe tends to dry out, and the Mediterranean region tends to become a lot more wet. If we look at the NAO index graph in the bottom, we can see the time scales that this is working on. So we're looking at phases of a decade or two.
Oscillation is an important tool for forecasting long-term weather patterns across the UK, particularly in winter. Now, the NAO itself is actually quite simple to measure. It's just the difference in pressure between 2 points over a period of time across the North Atlantic. Sometimes that pressure difference is high, and at other times the difference isn't so strong. And it's this variation that is the oscillation, the NAO. Now, this pressure pattern is the reason why we normally get westerly winds across the UK. When we've got low pressure here and higher pressure here, it means the winds tend to come in from the Atlantic. Now, the difference in pressure dictates how strong those winds are. And when we have a positive NAO, the difference in pressure is large. There's a strong gradient, and those westerly winds are that much stronger. So, they're bringing in mild air from the Atlantic, and that leads in winter months to mild and wet conditions and potentially stormy winters too. When the NAO is negative, that pressure difference isn't so noticeable. It's weaker. The westerly winds are weaker, and when that happens, it gives a greater chance for easterly winds to come in across the UK. Easterly winds in winter bring cold air, and so when the NAO is negative, there's a greater chance of a snowier winter. Now, it's important to point out that the NAO just gives an indication of the most likely pressure setup over a period of time. Any pressure chart on a given day would be different. But what the NAO does give are strong clues as to the types of winter that we can get. Recent studies have actually shown that our computer models are very good at predicting the NAO, and that's why it is one of the key features in the Met Office's winter forecast.
So I know that that was produced in the United Kingdom, and so it's a little bit different than what we would experience here. But this is just an example of another one of these internal variabilities that affect us here on Earth. similar to the North Atlantic oscillation, but operating in a circumpolar way as opposed to just over the North Atlantic, is annular mode. And annular mode comes in two different locations on Earth. There's the Arctic version and the Antarctic version, which are sometimes referred to as Arctic oscillation and Antarctic oscillation. And these tend to be the most important climate pattern in mid and high latitudes. So what are they? Well, just like NAO, annular mode is a difference in pressure between the Arctic and the temperate latitudes. If we have a small difference in pressure between the two, we are in the negative phase, and if we have a large difference between the pressures, we are in the positive phase. We experience annular mode in the most pronounced way when the index goes negative in the winter. So how does that actually affect us? Well, if we go negative, we can get hit by the polar vortex. When there's a large difference in pressure between the temperate and polar latitudes, that high pressure that's existing in the temperate latitudes prevents any of the cold air that's in the poles from escaping. If, however, that pressure difference decreases, that cold air in the Arctic no longer remains trapped there and can spill out and hit us farther south. So when you get hit by that polar vortex and you experience that, you're experiencing annular mode. You're experiencing it in its negative index. And that is happening when the polar vortex, which is a permanent feature, becomes weak. So when the polar vortex is strong, the polar vortex stays in the Arctic. So when you're getting hammered by cold, that means that the phenomenon is less intense than it normally is, even though you are experiencing very intense weather. There are other examples of variability within the climate. We've only looked at a couple. If you'd like some more, go ahead and click on this page and it will take you to a wonderful video about variability that you can use to supplement your education. So what is the impact of all of this? Well, because of all these different sources of variability, you can have weather experiences that differ greatly from year to year. Some years are much warmer in certain locations than others, and some years are much colder. And this is true despite the fact that the average global temperature does not vary that much from year to year. So let's take a look at the temperature anomalies for January 2011. Now, what does that mean? Well, remember that the temperature anomaly is a difference from an average. And so what we're looking at here is each one of these dots is representing how much warmer or colder it was in January 2011 compared to the Januaries from 1971 to 2000. And if you take a look at this, you can see that some areas are much warmer than average and others are much cooler than average. And this is the result of all of these different sources of variability that we've talked about today. You can look at this map and you can see whether or not we are in the positive or negative phase of NAO, or if we are in the positive or negative phase of Arctic oscillation. You can look at this picture and tell me if we are in an El Nino or La Nina year. What I want you to do is with your group when we get together to look at this map and be able to explain to me in the year 2011 which phase of each of these phenomena were we in. Today we looked at a lot of sources of variability in the climate system. And a couple of those you might be completely unfamiliar with, but they do help us understand when people are talking about cycles of events like hurricanes or cycles of drought or flood that you might experience out west. Hopefully with all that you feel like you're in a better place to understand how you can have some years that are warmer than others while still having an overall upward trend in temperature. Remember, you've got 2 things to do for homework this evening. I hope you all have a wonderful, wonderful day. We'll see you in class for Journal Club next time. Bye-bye, everyone.